Good morning, everybody, and welcome to CHE 156 class this morning. I hope you had a nice weekend and that long holiday. So we start from where we stopped. We're talking about J.J. Thomson's experiment to discover the mass to charge ratio of electrons. Remember, we started with William Crookes' experiment, which gave us the quantitative description, qualitative description of the electron. William Crookes' experiment gave us the description of the experiment. But to give value to some quantities, we started with J.J. Thomson's experiments that discovered the mass to charge ratio. Remember, we needed a figure. This particular quantity entity that we just discovered, which it was the electron as at that time, what is the mass? What does it weigh? What's the value of the charge on it? So that any other person elsewhere that finds the same thing will be sure that, oh, because this is the mass I got, then that means I got an electron, or as the case may be, other subatomic particles. So remember that these experiments are carried out in the 1890 something and so on. So it is the early 19th century, such that the available resources or apparatus there does not give room to actual measurement of electron. This electron itself is not something that can be isolated as at then. So we measured the mass to charge ratio through J.J. Thomson's experiment. The summary is what you have on your screen, where he balanced, he passed the cathode ray, which is now termed the electron, through a modified cathode ray tube, and he put them between both electric field and magnetic fields. I said the electric field, in an electric field, a charged particle, for example, if it was a positively charged particle, it will move towards the negative plates. This is the negative plate there. But since this is a negatively charged particle, it is deflected towards the positive plate. In a magnetic field, it goes in the opposite direction and it moves in a circular arc. So if it comes to the if the positive plate were here, in a magnetic field, it will be deflected towards the other direction. That's what you have here. That's the summary of what we did last week. Okay. So, and then we started with the calculation. In these calculations, we were trying to derive an equation that will give us our charge to mass ratio, where E, the small letter E, is the charge and M is the mass. The M was gotten from the centrifugal force. That's F equals to mv squared R. We did all this last week. We came up with the charge to mass ratio being 1.7586, approximately 1.7586 times 10 to the power 11 coulombs per kilogram. And yeah, somebody was asking, I said I omitted a line. Yeah, that's what you have there. I have already uploaded this on the LMS page, so I'm sure that most of you have seen this up to here. This is what I omitted, where you have the B, that's the magnetic field force or strength, B multiplied by E and V equals to mv squared. That in magnetic field, the electron moves along a circular arc such that the centrifugal force is equal to the magnetic field force. So if you do that, you have your E. If you make E over M the subject of this formula, you have V squared over BVR. I said one of these V will cancel out, so you end up with V over BR. I recall that we are, when we were dealing, we were balancing the electric field strength with the magnetic field strength, we ended up with this equation, V equals to E over B. Don't forget that. So if we put that, if you put where you have V over BR, if you put E over B as V, you will end up with E over B squared R. So please note that. Let's move on to the next experiment that was carried out. Since we now have a value for the mass to charge ratio, it was also good, research moves forward, progresses. We don't just stay there. So by the time it was the 1909, there was need to determine the actual value for the charge, that is the E. Please, I need you to listen. Stop raising your hands. Listen now, then you will talk at the end of the class. Don't distract yourself by just keep your hands raised. Please listen. I'm sure you can hear me because I have people around that are also listening, and I'm sure you can hear. So listen now, at the end of the class, you can raise your hand. I'm not going to entertain questions during the class. So let's talk about the questions after. But please listen so that you don't miss out completely. Thank you. So I was saying that there was need for improvement in whatever, you build up on whatever you have done. For example, if you do a project now, at the end of your project, they will ask you for suggestion for further studies. So you don't just end, research is not limited. So after we got a value for the charge to the mass, it will also be good to have a value for the E, that is the actual charge, and the M, the actual mass. And since it was impossible at that time to measure, because based on what is available, if you want to measure the mass, you have to weigh it. So there was no way to put the electron on a scale. So the first thing that was determined was the E. Since we know E over M, if we then know E, we have a value for E over M. If we know E, that means we can determine what M is. So the M was determined by Millikan using a Millikan oil can, and the experiment is termed as the Millikan oil droplet experiment. Millikan oil droplet experiment. So the first thing I'll do is to show us a pictorial diagram of the oil can, and then we'll discuss briefly the modus operandi, the modes of operation of the oil can. So this is a pictorial diagram of what that oil can looked like. Here you find an atomizer. Excuse me about that. So you have an atomizer at this end. This atomizer is something that produces atom size, that is tiny. It's able to turn any substance, liquid substance this time around, liquid, we need a liquid this time around, into atom size, tiny size. When I say atom, I'm talking about something that is tiny. So, and then there is a telescope at the edge of the, at this edge. That's what they have at that time to be able to monitor and measure the distance, the size of the droplets. So you see why we need an oil droplet. Now, inside this oil can, there are two chambers, and they are separated by plates. There are two chambers. The upper chamber is where the atomizer is, and then in the lower chamber we have two plates of electric fields. That's what you have there. That's a cross-sectional view of the Millikan oil droplets apparatus. So you have here an atomizer. This is an oil droplet. Water was not used because water does not. I mean, when it gets heated up, you know that it can volatilize and becomes hair. But for oil, and it has a little bit of density that can withstand this experiment without it becoming gaseous. So that's why oil was used. So what happened was that the oil was atomized, was turned into fine droplets. It was allowed to pass through this is a very, very, very tiny hole into the lower chamber that consists of two horizontal plates. Those are the plates. We have a negative plate and a positive plate. And an high voltage of electric current, this one is showing it as an X-ray, but high voltage of electric current, these are electric plates, was passed through the plates so that these uh, oil droplets can uh, accept charges, which are electrons. That's what we expect them to. The charges are going to be the electrons that we are talking about. Now, normally the oil droplets are supposed to be falling down due to gravitational force. But the high voltage is applied in the measure that will make the electric field force balance the gravitational force. The electric field force that was applied will balance the gravitational force such that the oil droplets become temporarily or momentarily suspended in the mid-air. It becomes temporarily or momentarily suspended. And at that time, the telescope can then begin to use to measure the size of the droplets or whatever. And we will see the calculation just in a bit. So that's what you have here. The summary of what I've just said. The oil droplets apparatus has two chambers. The upper chamber has an atomizer. Don't be too agitated about this. As you know, after the class, I'm going to post this notes so that you can go over it again. So the atomizer disperses a fine mist of micro-sized oil droplets, and the oil droplets falls through a pinhole into the lower chamber consisting of horizontal electrical plates. Then there is a window beside the oil can that allows the droplets to be viewed through a telescope. This is just a schematic diagram of the experiment, everything that has been, and you can see the voltage being applied. Now, all this has been. So let's go to the actual mathematical calculations. Then we'll go on from there. Let's go to the mathematical calculation on there. So now I want you to please follow me very well. When the droplet, please pardon me, I'm thinking, I hope you can all see my slide. I hope so. When the droplet is suspended, its weight, remember what weight is? The weight is mass times gravitational force. The weight is equal to the electric field force. That is, when it is suspended, the weight is equal to the electric field force. That's the electric field force there. Obviously, we have it as the strength, capital E, multiplied by the charge. But now we have Q. I would define what Q is in a bit. But the M is the mass of the oil droplet. G is the acceleration due to gravity. E is the electric field strength we are familiar with here. But Q now Q is the total charge of the oil droplets, because each oil droplet is capable of taking more than one electron. So we now have to introduce N to multiply the number of electrons that is measuring, that each oil droplet captures. So Q is actually charge, but it is now the total charge. So instead of having E multiplied by the small letter E that has been for charge, we have E multiplied by Q. That's what you have there. So you have EQ. There Q is Na. So if you, and you have N to be number of electrons and Q to be the actual charge on the electron. Thus, if you now estimate the total charge Q, you have Q to be mg over E. From this equation, if I make Q the subject of the formula, we have mg over E. So now, the mass of the oil droplets, the gravitational force, of course, is known, is constant. The mass of the oil droplets can be measured through the telescope, the size, and eventually the mass. The size of the droplets, the mass can be determined through the telescope. The electric field strength can also be determined. You know, the amount of electricity or the voltage that was passed, that can be determined. So everything that is on this right side of this equation, everything on this right hand side can be determined. So that is why we are able to determine the total charge on the oil droplets. So invariably, from the values of Q that was obtained, the actual value of charge E on the electron was estimated to be 1.602 times 10 raised to power minus 19 coulombs. We're not going into the details, too much details of the experiment. By what we have explained so far, you are familiar with what exactly was done and how it came to be. So we are Millikan determined the actual charge to be 1.602 times 10 raised to power minus 19 coulombs. Remember, we know the value of E to M. That was what J.J. Thomson determined. Value of E over M is 1.756 times 10 raised to power 11. Now we have a value for E. That means we can therefore determine the mass of the electron. So the mass of the electron was determined to be 9.11 times 10 raised to power minus 31 kilogram. 9.11 times 10 raised to power minus 31 kilogram. And you can see that this is very light. Note times 10 raised to power minus 31. So that's like 0.0000 in 30 places before you get to 911. So it's a very light. So at the time of this discovery, it was found to be approximately 2,000 times lighter in weight than the first known lightest element, which was hydrogen. As at the time, hydrogen was the lightest element that was known. And it was discovered that this is approximately 2,000 times lighter. It's very light. And that explains what J.J. Thomson observed, that about the penetrating. No, sorry, that's not J.J. Thomson. Beg your pardon. That's William Crook. What William Crook observed about the penetrating abilities. I'm going to correct that. It was William Crook that determined the qualitative properties of the electron. So one of his observations was that the cathode ray, which is the electron, was able to penetrate small thickness of material. That's one of the characteristics. So please note that. So let's look at practice question. We have this in page, you have this on page 37 of your Fundamental of Physical Chemistry. One of the questions there, let's solve it together. In this question, we are told that an experiment to determine the charge to mass ratio of the electron was performed twice with the same cathode ray tube. In the second experiment, the magnetic field strength was double that used for the first experiment. By what factor must the electric field strength be changed? Let's take that in for a while and try to interpret it. You know, the cathode ray tube was used to determine the charge to mass ratio. So somebody was trying to determine the charge to mass ratio, and I told you that the what J.J. Thomson was doing was trying to balance. He would increase, he was trying to balance the electric field strength and the magnetic field strength. So if he applies a particular amount of electric field strength, he must use a particular amount to balance it. So in one experiment, he used a particular amount of electric field and magnetic field. In the second experiment, this scientist doubled, he said the magnetic field strength was doubled that which was used in the first experiment. So by what factor will the electric field strength be changed? So let's be patient to see the solution. Recall that the charge to mass ratio is given by this equation. I'm sure this is no problem for any of us. E over m, that's the charge over mass. That's what we call charge to mass. Is a ratio, is a fraction, so is a ratio. Charge to mass is equal to E, the capital E, don't forget what it is the electric field strength. B is the magnetic field strength. So it's B squared R. R is the radius of that circular arc. So in the first experiment, let's say the magnetic field strength is B and the electric field strength is E, the way we have it. So in the first experiment, this would look like the equation. This one you are okay with. So we are talking to that particular question now. So let's say this is what we have in the first experiment. This one is okay. So in the second experiment, we are told that the magnetic field strength was double that which was used in the first experiment. So if in the first experiment, the magnetic field strength was B, since it is double, in the second experiment, it is 2B. In the first experiment, the magnetic field strength was B, and the question says that the magnetic field strength was doubled. So we now have 2B. And we are supposed to determine what the electric field strength will be. So since we don't know the factor by which E has increased, because that's what they say you should determine. The question says, by what factor must the electric field strength be changed so that we can have a balance? So let's assume that the electric field strength is X. So what we have there is E over M will now be whatever the electric field strength over this. Remember, this one is typical of any experiment that has to do with cathode ray tube. It will always be the electric field strength over the radius, whatever the radius is, multiplied by the magnetic field strength squared. In this second experiment, the electric field strength is X, the magnetic field strength is 2B. So wherever you find E, you put X. Wherever you find B, you put 2B. So we have X over R4B squared. Since equation 1 and 2 are similar. Why are they similar? They both end up being E over M. That left hand side of the equation is E over M for the two of them. E over M here, E over M there. So we can then equate equations 1 and 2. We can equate the right hand side of equations 1 and 2. So if we equate equations 1 and 2, we have the right hand side, we have E over R B squared equals to X over R 4B squared. Now we can now begin to remove some things, B squared will go, R will go. So we'll end up with E equals to X over 4. E equals to X over 4, such that X will be 4E. That's the electric field strength will be 4 times E. Remember, E in this case is what you have for the first experiment. So to answer the question, if P is doubled, E must be quadrupled, that is multiplied by a factor of 4. The question says by what factor must the electric field strength be changed such that we have a balance between the electric field strength and the magnetic field strength. So if B is doubled, E must be quadrupled. You can look at further examples all around and try and solve. Let's quickly go to the next. Like I said, we'll take questions after the class. So it will be good if you let's not distract the class with raising hands if you would wish. So discovery of the proton, quickly. We will not go into too much details because it was a similar thing that was done in the discovery of the electrons. Here, it was Goldstein that used a modified cathode ray tube. Note the word, he modified the cathode ray. This is similar to what William Crook did, but in this case, and then that means it was still passing gas at low pressure into a modified cathode ray tube, and you observe new types of ray. This time around, they were attracted towards the negatively charged plates, hence they have positive charges. So these ones are not, they are not emanating from the cathode. So they are coming from towards the negatively charged plates, unlike that of the cathode ray that was coming towards the positively charged electrode. So they are called the canal rays, not cathode rays this time, or anode rays. And later, they were called protons. The charge to mass ratio were also determined as case of electrons, and it was found to be much lower than those of electrons. The magnitude for the charge was also determined and was found to be 1.672 times 10 raised to power minus 27 kilogram. 1.672 times 10 raised to power minus 27 kilogram. Remember, for electrons, it was 9.11 times 10 raised to power minus 31. So these are a bit heavier. The protons are a bit heavier. This times 10 raised to power minus 27, whereas that one was times 10 raised to power minus 31. So the protons are a bit heavier, but still light. They are light. That's times 10 raised to power minus 27. So, I mean, in charge, that's the charge anyway. Sorry, that's the mass. So this is what you have for the diagram to represents a modified cathode ray tube. And you can see that the direction of the ray is now in opposite direction to what we saw during in the cathode ray. It's coming from the anode. That's why they are called anode rays. And you can see that the cathode has been perforated. And you can also note that air in the tube is still at low pressure. This will lead us to the next line of story in the discovery of subatomic particles. So now, electrons have been discovered. They have been we have a value for their mass and their charge. So also proton had been discovered, and there is a corresponding values for them too. So it was assumed that, oh, since we have electrons and protons, something that is positively charged and negatively charged, that means we have all that is inside an atom, because an atom is a neutral entity. So what else do you need? You need a positive charge, you need a negative charge. And since all these have been discovered, so people started proposing atomic models. One of the first models were proposed by J.J. Thomson, and he proposed a plum pudding model. Now, these are proposals, and each of these proposals are subject to experiments, researches, so as to ascertain whether whatever it is that was postulated subsists. So J.J. Thomson proposed a plum pudding model. What's a plum pudding? I know we are not familiar with pudding so much here in this part of the country, but I'll show you in the next slide what may help us. But what he's saying invariably is that it was postulating that an atom consists of negatively charged electrons that are swimming or floating a sea of positive charges. So it's either of these model. That's what is postulation. That the main backbone of the atom is positive charges, and we have electrons floating inside them. So that's what we call it. This is what a pudding looks like. Anyway, what you have on top here is a pudding. Now you get what they are saying. So the plums are inside. Those black things are the plums that are inside the pudding. So that's what you have. But I say if you don't understand that, you should understand granules swimming inside gari. So let's say the granules are the electrons and the gari are the protons. That is his model. So that's what he postulated. So to ascertain this, people carried out experiments, and one of the experiments to ascertain the model or the constituents and arrangements of the subatomic particle was done by Rutherford. To test this model, Ernest Rutherford performed what he called the gold foil scattering experiment. The gold foil scattering experiment. In this experiment, Rutherford put a thin shield of gold foil in between a beam of alpha particles and a recording plate. So he bombarded the gold foil with alpha particles. Alpha particles are fast moving positive charges. And he made 3 different observations, summary of his observation. The most key important ones were that most true. Remember, what he's trying to find out is what is inside the atom. So when you add a gold foil, that's an atom of gold. So the gold foil is made of several gold atoms. So that's what we have. So a gold foil is made of several gold atoms. Remember, any element can be broken down into atom, and atoms will now go to the subatomic particles. So when he bombarded the gold foil with fast positive charges, he observed that most of the rays pass through, and that has a meaning, because what he had in his mind was the J.J. Thomson's model, that we have a sea of positive charge, and then we now have negative charges moving. If it was a sea, if you bombarded it with positive charges, if positive charges hit positive charge, what do you think will happen? It should rebound. It should repel it. So, but the fact that most of the rays pass through without deflection means that that model is not correct, because he expects a reflection or a rebound. Now, very few of the positive charge of the alpha particles, very few of them were deflected through large angles. Now, this could mean a lot of things, but one of the most important things it could mean is that, okay, since they were deflected, that means they were close to a positive charge, and then instead of passing through on a straight line, they got deflected. So the positive charge is what is deflecting them. So, two positive charges will not attract. Then lastly, some rebounded. Now, the ones that rebounded means they must have hit something very solid, something hard and positive. This is a schematic diagram of Rutherford's experiments. This is an alpha emitter, and that's the gold foil, and that's the detecting screen. You can see what I just said. Many passed through, many of the alpha just passed through. Some were deflected, and few of them rebounded. Looking at a closer view, these are the gold atoms, and you can see the alpha particles coming. Many of them pass through. Some will pass through with deflection. These ones are deflected. You can see they are not passing through. And you see that they get deflected when they are close to that center. But at this time, he doesn't know. He's interpreting what he sees. So it's not as if he is sure that he's at a center. But now we know what is happening. He's interpreting his results. And then he found that few of them got, rebounded back. Conclusion from Rutherford's experiments is that the fact that some of the alpha particles were deflected or reflected means that the atom had a center that's concentrated with positive charges. And the alpha particles had either hit the positive charges directly. If they hit it directly, it will be reflected or rebounded, or passed close by it, so that the positive charges causes deflection. And since many other particles pass through the gold foil without deflection, it means that the place that is actually positive in the atom has to be very small, because many of the alpha particles pass through without. So that gave rise to the fact that the positive center will have to be a relatively small to be relatively small size compared to the rest of the atom, meaning that the atom is mostly open space. So this one is just a brief highlight of the conclusion. So the same thing I said in the. Now, it now began to generate interest that how could protons, or as it is now, as at that time, how could they come together at the center? They are supposed to repel themselves, but it has been found out through this the Rutherford experiments that they actually they are able to form a core center. So that means there must be something now. It can't, we have found that it can't be electrons. It can't, and you either have protons, electrons, those are the charges you have. So since you have positive charge, you have negative charge, then, and you know that the atom is electrically neutral. So that gives rise to the postulation that there must be something that is neutral, that is not negatively charged, that is inside that core center, that is helping the protons to bound together. And that is what you have in this side, that Rutherford was the first to propose an electrically neutral entity to make up for the residual mass of the nucleus. So the significance of the electrons is just, number one, to strongly bind the protons, which cannot bind, will not be able to bind to each other due to electromagnetic repulsion. That's understandable. And it also keeps the atomic nucleus from flying apart because it's heavy, and it constitutes the major mass of the atom. A summary of all the subatomic particles is given. We have the nucleus containing, that's the center. We call it a nucleus because it has been proven that the positive charge is concentrated inside the center. We have their charge, their the relative charge, because these charges are actually small. Now, note that the charge, I talked about the mass, though the mass of the electron and the protons are different, but their charges are about the same. It's just that one is positively charged and the other is negatively charged. Then the mass, we have talked about this mass. And you can see that the neutron is just a little bit slightly heavier than the proton. But these masses are, these values are very small. Before you can start writing times 10 per minus 19, I mean, using it. So that's why we have room for relative charges. So on a relative scale, proton has a charge of +1. This is the actual charge, plus 1.6 times 10 per minus 19. That's the actual charge. But it has, on a relative scale, it has a relative charge of +1 and a relative mass, atomic mass of 1. But this is the actual mass, relative, because this, you can't start writing this. And you can see that the nucleus is just a little bit heavier than the nucleus is, the neutron is just a little bit heavier. So we go to the number of protons in the electrons, number of protons in the atom. I'm sure that this is something you are familiar with. This cannot be strange to most of us. The atomic mass and the atomic number. It's just like a recap of what you already know. So I'm not going to go into details because we have a lot to cover in this segment in our next class. So all this you will see in your notes just for you to brush up. Atomic number is either the number of protons or the number of electrons, not number of protons per electrons. Is either the number of protons or the number of electrons, because an atom is an electrically neutral entity and it will contain the same number of protons and electrons, except when it is not neutral, maybe when it is charged. So as long as it is not charged, it will contain approximately same number of protons and electrons. And the atomic number is usually represented by the symbol Z, whereas the atomic mass is represented by A, and it is the addition of the number of protons and neutrons. Addition of number of protons and neutrons. So you are familiar with these notations where you have the mass number being the summation of the number of protons. Yes, protons, which is the atomic number plus the neutrons, and Z being the atomic number, that is the number of protons or electrons. An example is given here. I won't go into these details because we are familiar with it. What we need to now talk about, and that is important to us, is the concept of isotopy. Isotopes, that is when elements do not have the same the atoms of the same elements, like that gold I showed us the other time. Gold inside an element of gold, you are supposed to have atoms of gold, and each atom is supposed to have the same number, the same mass number, the same atomic number. But you find out that there's elements that have different atomic masses. They will still have the same mass, atomic number, but they have different atomic masses. And this is due to differences in the number of neutrons. Since electrons and protons are the same and they have the same atomic number, so that means the number of protons and electrons are the same. But since they have different atomic masses, the only thing that can be different is their number of neutrons. So I will give room for, this is what we start talking about in our next class: isotopes and relative atomic masses. So that's what we start talking about in our next class. So I give room for a few people that wants to, a lot of people have their hands up. So let's see. Oladipo John, if you are still here, I've asked you to unmute. Can you ask your question?
Good morning, ma'am. Hello.
I can hear you.
Please, ma'am, in some textbook, the charge to mass ratio is given as minus 1.76 times 10 raised to power 8 coulomb per gram. Is it correct?
Please stick to what I give you. The charge to mass ratio cannot be minus, cannot be negative.
Okay, ma'am.
Stick to what I give you. Thank you.
Okay, ma'am.
Please, can you kindly mute so that it doesn't cause distraction? I appreciate that. Akim Aziz, I have asked you to unmute.
Good morning, ma'am.
Good morning, dear.
Yeah. Please, ma'am, could you please help us to upload the slides on Moodle, ma'am?
I can't hear you. Please, can you speak louder? Sorry.
Please, could you please help us to upload the slides on Moodle, please?
I should help you upload what?
The slides that you are using, ma'am.
I told you that it will be uploaded after the class. I will always upload my slide after my class.
Okay, ma'am. I didn't hear that. Thank you, ma'am.
Yeah, I will. But did you get the last slide?
I've not really checked, ma'am.
No, it's because you have not checked. I've uploaded this since last week.
Okay, all right, ma'am. Thank you, ma'am.
I will upload this just today's class after the class. Thank you. Can you mute? Thank you. Let's get a Bisiriyu. I'm the lats. Your hand is raised. Can you unmute and ask your question? I've asked you to unmute. Okay, I don't think she's there again. Okay. Samuel Oyelami, I've asked you
Good
to
morning, ma.
unmute. Okay.
Good morning, ma.
Good morning.
Good morning. Okay, I have a question concerning the generation of canal ray, the protons from the anode.
Yes, dear.
Okay, from the diagram, I saw that the tube was connected to electric source. So
Yes.
I want to ask that when the tube is connected to the electric source,
Mm-hmm.
that means electricity is carried through the tube
Mm-hmm.
by the electrons. So I want to ask that
It's
how
not it's not okay. Go on.
I want to ask if electrons are if electrons are the carrier of electricity in this form. So how are protons being generated from the anode?
It's not all the time that it is electrons that are carriers of
Hello, ma.
electricity. Hello, can you hear me?
Oh, yes, I can hear you, ma.
Hello? Can
Hello,
you
I
hear
can hear
me?
you. Yes, ma.
Okay. Okay, thank you.
All right,
It's not all the time that it is electrons that are carriers of electricity. That's number one. Electricity
all
can
right,
pass through the wires. Remember, the experiment itself is passing electrical charges through uh, gases in a sealed
all
tube
right.
under low pressure. That is the
Yeah.
experiment.
Okay.
Passing electrical charges. And that is why
Okay.
you have a cathode and the anode there.
All right.
Passing electrical charges in a sealed tube. That's the so what they are observing is what is happening to the gases. So the
Okay.
observation is what is happening to the gases. So different when I mean gases, the gas will represent an element now, an element in
Oh
its gaseous
yes.
state. Hello, can you hear
Okay.
me?
Yes, I can hear you, ma. Hello, ma.
So the is passing electricity into different gases under low pressure. So that's the
Pressure. All right.
experiment. So the experiment is to observe what is happening to the gases. And it was during that Crook observed that a ray comes from the cathode and goes to the anode. And it was in that same way that the observation of the canal rays from the anode or
All right.
anode rays, anyone to the cathode. So it is
Okay.
what is happening inside the gas, to the gas
Okay.
that we are monitoring. It's not, we are not looking at the electrons. So it was not the
All right.
electrons that is carrying the charges. If
But
you
ma,
have,
hello, ma.
yes, please, I'm listening.
All right. So I want to know exactly where the protons are being generated. You know, before the protons can be generated from an atom. That is, the protons must have broken off from the nucleus. And before we get to the nucleus, we must first, we have the orbital of the electrons, the electron orbits. So I think I want to know how exactly the protons are being ejected out of the nucleus now.
We,
Why
I,
not the
from the
electrons?
cathode ray experiment,
No, I mean that
from the sorry,
protons.
anode experiments.
Yes, ma.
So now, in your own view, the
Okay.
ray that is coming from the anode and
Yeah.
going towards the cathode, this time cathode has been perforated, so we are not even minding looking at the ray. It's already a perforated tube. Remember, it's perforated. So
Yes, ma.
now the ray that is coming from the cathode going towards from the anode going towards the anode, what charge do you think it should
Cathode
be?
from the anode, ma.
Yes.
Is that okay? That should be the protons,
I said, what charge? So
ma.
the experiment here is to determine how it was broken. How do you think that even in the case of the electrons, do you think electrons will just fly out? The fact that it is electrical charge that is being high voltage that is being passed through nucleus.
Hello, ma. Hello? Hello, ma. Oh, hello? Hello, ma. Can you hear me, ma? Oh, God.
I'm sorry about that. I lost my internet. That was what happened. And I think we are actually done with the class. Sorry about that timing. So see you next class. Look for the notes immediately after this class, maybe like